Hi everyone, welcome to Lecture 10. So these are some of the topics that you'll be expected to know after this lecture, lecture number 10, about the design of scientific studies. Okay, so just backing up a little bit, in this course, what is this course about? Are we learning statistics or what? I want you to keep in mind that there are many, many types of statistical tests in the world, and the choice of tests that you use when you're doing research depends on your scientific question and it depends on the type of data you have. But new statistical methods are being developed all the time. For example, we have the rise of machine learning in the past decade or so, and we have lots of new tests being developed for new types of data and the very large data sets that modern research has. So the goal of this course is not to get you to memorize lots and lots of specific tests that you might soon forget. Instead, what we want is for you to develop a foundation of statistical literacy that's going to support all of your future learning. Once you have those basic principles, you have the ability to teach yourself about specific types of analyses. And I want to use an example of a very famous biologist who said about math that it was repugnant to them. This person really disliked math, did very poorly in math at school. I'm wondering if you know who that was. It was Charles Darwin. He really did poorly in math, and yet he did many careful quantitative studies. And Darwin even invented some of the sampling techniques that are still used in statistics and in biology today. As an example, he pioneered the use of quadrat samples, which are when you want to sample an area of landscape, quadrats are like little blocks that form your units of a sample. And so he invented that and he used that to measure the diversity of plant life in his own backyard. So he was bad at math, but he thought a lot about variation. He spent decades thinking about it and he developed a statistical intuition. And so it's that intuition for variation and randomness that's really what I want you to gain from this course, is the kind of understanding of those processes that underlie all of the fancy techniques that are being developed. Okay, so even though statistics as a word didn't exist when Darwin was doing his work and didn't exist as a discipline, he had that intuition. All right, so today's topic, study design, confounds, and why good study design matters. Okay, so some terminology to set you up. You probably have heard some of this before in high school. We've got the dependent variable and the independent variable, and we've got some synonyms, some words that mean the same thing. So the outcome variable that we're interested in is called the dependent variable, the response variable, or the outcome variable. The thing that we hypothesize might be causing variation in the outcome is called the independent variable, the predictor variable, the explanatory variable. So we've got cause and effect, right? These two crucial variables in some hypothesized relationship. When we graph those two variables, we often put the causal variable, or the one that we propose is causing the other one, on the x-axis, and we often put the outcome variable, the dependent variable, on the y-axis. We covered that last week. Okay, so just to clarify those definitions, the dependent variable is the one that you think will be affected by something else, and the independent variable is the one that you think is doing the affecting, the thing that you think influences the dependent variable. So it's really important to have this terminology straight. Okay, what is a confounding variable? A confounding variable is an extra variable that you didn't necessarily account for, maybe that you should account for, and that influences the other variables that you're investigating. Confounding variables can make it difficult to interpret results. Confounding variables can influence both the dependent variable and the independent variable. A confound might influence one of them, the other, or both. And if you don't consider a confounding variable, you might be misled. And we're going to look at a surprising example of that on the next slide. So good study design involves thinking carefully about potential confounding variables so that we can do our best to design a study that will avoid misinterpretation about what's going on. Okay, so this is a really well-known example with real data on students who were admitted to Berkeley University in 1973. So Berkeley was studying its admission process in that year, and they wanted to make sure that their process didn't have any gender bias. And so the administration looked at this data. They had numbers for how many men and women applied to Berkeley in 1973, and they had numbers for how many men and women were admitted. So this is a real example. And when you calculate the proportions, what they found was that over 50% of the men who applied were admitted, but only 40% of the women who applied were admitted. So this looks bad. This suggests that men are perhaps being preferred in the admission process as compared to women. And so this was potentially a real problem if that was correct. Okay, so if you break it down by department, a very different picture starts to emerge. Okay, so in this table below the front top line there, when we have by department, we have these 4 departments, A, B, C, and D. These departments are things like biology, engineering, arts, and English. And what we have is the number of applicants and the number admitted and the percent admitted for men and women in each of these departments. And if you look closely, what you see, if you look at like A, you can see that 80% of women were admitted, 82% of women were admitted, and yet only 62% of male applicants were admitted. And if you look at Department B, 68% of female applicants were admitted, 63% of men. And for Department C, slate favor for men. We've got 37% of the male applicants admitted, 34% of women. And for Department D, again, we have a slight bias in favor of women. 35% of the women applicants were admitted, 33% of the men. So this is paradoxical. Overall, at the aggregate level, it looks like there's a big bias in favor of admitting men. But when you break it down by department, 3 out of these 4 departments have a bias in favor of women, and the only one that has a bias in favor of men is pretty slight. So how can this be? Well, I assure you that the numbers in this table are correct. You could pause the video and do the counts yourself. It really does add up. So what is going on? How is this possible? Well, as a hint, there's ways that these departments differ, right? So what do you notice about differences between these departments in terms of the data that's presented here? Pause the video and think about that for a moment. What we have going on is confounding. So these departments differ in a couple of factors. For one thing, they differ in how easy they are to get into on the whole, right? So Department A is a lot easier to get into than Department C, Department D. The departments also differ in terms of the number of male and female applicants that they attract. And so we've got these confounding variables of these other features of these departments. And it turns out that the most difficult to get into departments are the ones like Department C, are the ones attracting the most female applicants. Whereas the Department B, that's really easy to get into, it attracts a vast majority of men. And I think Department B is like engineering, and C and D were like kind of humanities departments that were very selective at that time. So it's not that men were being favored overall. It's that the departments that were admitting the most applicants, the ones that were easiest to get into, were also the ones that were attracting the most men. So we've got confounding variables that explain this aggregate pattern. And it's really important to understand that in order to fix this, to address this issue, right? To understand why are fewer women being admitted into Berkeley at that time than men. Okay, so a couple of quick practice questions. We'll take this up on Zoom. Some scenarios here. I just want you to write down what is the dependent variable and what is the independent variable in each example. All right, so example number 1, we have a research question. Does exercise affect grades in biology courses? we have a hypothesis, and we have a prediction that people who regularly exercise will have higher grades and those who lack exercise will have lower grades. Example number 2, our research question is, why do students have bad dreams? My daughter had some very bad dreams the other night and kept me up half the night. You might have a hypothesis, I've heard this before, that eating cheese right before you go to bed might cause bad dreams. And you might have a prediction. Students who are fed cheese before bedtime will have more bad dreams than another group who are fed something else as their nighttime snack. Okay, so now for those 2 different examples, what could be some potential confounding variables? Can you brainstorm some potentially important confounds in this grades example? And can you do the same for this study of dreams? All right, so we'll talk about that on Zoom. So what do we do to handle confounding variables? Well, the first step is to identify them like you just did, and to think about how to reduce their effect on your study. For example, that might involve measuring the confounding variables from your participants in your study and ensuring that your samples or your groups do not differ in terms of the confounding variables. As an example, if you're studying something that might be influenced by gender, you might want to make sure you account for gender as a potential confound by surveying an equal number of males and females. So that could be done with stratified random sampling. In an experiment where you might be assigning your individuals to treatment groups, it might be important to check that your treatment groups don't differ on average in terms of the confound. And we'll look at examples of that later on this week. And you may want to introduce controls to eliminate variation in the confounding variable. For example, maybe you're studying something where age is expected to influence the process you're interested in. You might want to control for age by only including people of a certain age in your study. That has its own drawbacks, of course. Alternatively, you might include people of lots of different ages, but you might assess their age as part of your methods, and you might include data on age in your statistical analysis to specifically address whether it has an effect. And as a last point, not everything can be controlled for ethical and practical reasons. Obviously, we can decide whether we want to sample people of different ages, but we can't control someone's age. We can't control someone's gender. So why does this matter? Why do confounding variables matter? Well, we need to design our studies well to get results that are useful and reliable. And in the past 10, 15 years, there's been some alarming reports that a lot of studies in biology and medicine are not reproducible. For example, the pharmaceuticals company Bayer revealed in the last decade that they ran their own studies inside the company. They do that all the time to develop new drugs, but they ran studies to try to replicate some of their previous studies, and they found that about 2/3 of their previous studies could not be replicated. When they repeated the study a second time, they didn't get the same conclusion. That's very alarming. This is data from a survey run by the journal Nature, surveying over 1,500 scientists and asking them, is there a reproducibility crisis in science? And over half of the researchers surveyed thought that yes, there is a significant crisis. I'm not sure what a slight crisis would be. It sounds like kind of an oxymoron, but another 38% of people in the survey thought that things were definitely not good. So why do so many studies get things wrong? Well, this is a big question, and there's not one answer. We've already looked at a few of the reasons so far in this course. We've seen how having a really small sample size can introduce more error into your estimates. We've seen how biased sampling can introduce error into your estimates. And we've seen how mistakes and bad data hygiene can introduce errors. There are a couple of big misconceptions among students, among researchers. One is that it doesn't really matter how you collect your data. There's going to be some statistical flourish that will fix that problem and allow you to use the data. Well, actually, well-designed studies are simpler and more straightforward to analyze, and poorly designed studies are often useless. Another myth is that if you can just collect enough data, if you just get more data, you can be more confident about the results. Well, it's true that larger sample sizes are better, but quality is essential. If a study is so poorly designed as to be irrelevant to the question, it doesn't matter how much data you collect. And we saw that early in this course where we looked at the example of the election poll from the early 1900s that had millions of Americans polled and still got the prediction massively wrong. So there's no statistics that substitute for poor design. So the solution is you have to know your research question and think carefully about your hypotheses and predictions. And those hypotheses and predictions dictate what you measure, what your target population is, how you collect your sample, and how you perform your analysis. And why does all of this matter? Well, there's lots of reasons. Doing studies, poor studies are a waste of time, and that's a lost opportunity to learn something important, right? Because the poorly done studies don't really tell us anything useful. They're a waste of money. They're they're detrimental ethically, often because humans and animals might be involved in research, and it's not ethical to cause suffering or cause stress in humans and animals for research that's not reliable. Studies that are poorly done and then get published might also influence other studies and cause other researchers to go down paths that aren't particularly fruitful. So those errors have a cost beyond the single study. And of course, there's personal costs to designing studies poorly. It can be embarrassing or hurt a researcher's reputation. Here's an example of the very real cost of poorly designed studies. You might know that measles can be a very dangerous disease to small children. And so in Canada, children get vaccinated with the measles, mumps, and rubella vaccine in the first couple of years of life. And in the last century, around the time when I was growing up, measles was declared eliminated in the United States. Okay, so the more and more vaccine programs got rolling, eventually the disease wasn't occurring anymore in some parts of the world. But in 1998, a British doctor, Andrew Wakefield, published a scientific paper in a prestigious journal called The Lancet. And the paper proposed a connection between the measles vaccine and autism, the development of autism in young children. And this paper got widespread media coverage. And in the years afterwards, immunization rates in the United Kingdom really plummeted. And this study really sparked a lot of vaccine hesitancy all throughout the Western world. The really unfortunate thing was the study was terrible. It had only a sample of 12 children. And later investigations by other people would reveal that the doctor, Andrew Wakefield, was getting paid by a lawyer who was working on a lawsuit against a vaccine producer. So he had a real conflict of interest. And they also found that there were errors in the data. In that really small sample, the data were not robust. And there have been several follow-up studies in the decades since that were involved much larger samples, were much more higher quality, that showed that there was no link between the measles vaccine and development of autism. Okay, however, this graph is showing you the number of measles cases across the years in the past 2.5 decades. And you can see how measles has really resurged. So there's been increasing cases and many outbreaks in the last 5-6 years. And that has a real toll in terms of deaths for some young children. Okay, so I want to talk about the difference now between observational studies and experimental studies, and then we'll briefly touch on some other types of studies. And we're going to look at a hypothetical example of a real research question. The research question is whether exercise can cause university students to perform better academically. So that's a really important question. Understanding the factors that influence academic learning can help us design better university programs um, and really promote students' careers. So we might have a hypothesis that physical exercise influences academic performance, and we might have a prediction that students who get more physical exercise should get higher grades. Okay, we can test that prediction in multiple ways. We could design an experimental study, and that's where the researcher directly alters the key independent variable of interest and then measures the effect that this has on the dependent variable. Alternatively, we could design an observational study, and that's where we look for an association between naturally occurring variation in the independent and dependent variables. So I'm going to walk you through how each of these two major types of studies could be done for our hypothesis in the next few slides. The experimental studies are often called manipulative studies because we, as the researchers, manipulate the variable of interest, the independent variable of interest. Whereas observational studies are often called correlative studies. Okay, so let's pretend we want to run this observational study of this question. And let's say we're going to begin with a random sample of N students from Carleton. And this is an observational study. Our independent variable here is their physical exercise. So we need to measure that independent variable. And you could think about possible ways you could do that. Maybe you could use devices that will monitor their physical activity throughout the day. Maybe you could survey them about their physical activity. Maybe you could use the fact that the gym at Carleton is a major source of physical activity for a lot of students and track their usage. And what we want to do is observe them for the semester and quantify that physical exercise and also quantify their grades in their courses. Their grades is the dependent variable here. Okay, important to note, we did not manipulate the key independent variable here. Instead, we're using the naturally occurring variation in exercise behavior to look for a relationship between exercise behavior and grades. Okay, so what other variables should we measure? What are potential variables that might influence exercise, grades, and possibly both? These are potential confounds, and it's important for us to think about how they might affect our study. So we could brainstorm some of these, maybe a student's overall level of motivation, maybe other things that they need to do with their time, like whether or not they have a part-time job. I could envision how having a job would influence both your time available to study and your time available to exercise. We could measure what other commitments they might have. We could measure the amount of time they spend on campus, their program of study, maybe the type of exercise they do is an important variable that could influence the effect of exercise on grades. So we'd want to know what kind of exercise were they doing. So all important confounds that we might need to think about. All right, so let's form a data prediction. What would be the evidence that we would expect to support our hypothesis that exercise can boost a student's grades? What would that look like? Well, it would depend on how we chose to measure our variables. If we chose to, for example, measure the number of hours of exercise per week for each student, and say we have a sample of, there's probably like 25 students here, we might evidence that would support our hypothesis might show that the students who have more hours of exercise per week have higher average grades on their final exams. Alternatively, we might measure exercise as a categorical variable. Maybe we define students who exercise as those who get at least, let's say, 2 hours of activity per week, and students who do not exercise as being those who get less than 2 hours of activity per week. That's just one way you could imagine. There's lots of ways you could define that, but we'd have to pick a way, and you could imagine how you could graph the data looking at the distribution of exam grades for students in these two categories. So both of these scenarios would support our hypothesis that more exercise is good for a student's grades. Now, just as an aside, what is a correlation? A correlation is a type of statistical analysis that we use to quantify the relationship between two numerical variables. Below, I've illustrated 3 scatter plots. We've seen them in the recent lectures on data visualization. They show a relationship between a numerical variable on the x-axis and a numerical variable on the y. And I've got 3 scenarios here. One where these two variables have no correlation, and that's where there's no consistent change in the outcome variable when the independent variable changes. In the middle of the slide, I've depicted a negative correlation, and that's when the independent variable increases, the outcome variable decreases, right? So you can see how as you move along the x-axis, you get higher and higher values of x. We're getting lower and lower values of y. And lastly, we've got our positive correlation. That's when the independent variable increases and the outcome variable increases. Okay, so you can see on the very right-hand side of the slide, as we get higher and higher values of x, we also get higher and higher values of y. So this is important terminology, just as an aside from what we were talking about with the exercise example. And I want you to be aware that observational studies are sometimes called correlative studies, but an observational study doesn't necessarily have to have a correlation test. One of the variables in an observational study could be categorical, and in that case, we wouldn't be looking at scatter plots, we'd be looking at box plots and things like that, and the analysis would not necessarily be a correlation test. Okay. So let's look now at how we could study the same research question using an experimental study where we do a manipulation of our key independent variable. So again, we need a random sample of n students at Carleton. We still need to measure any confounding variables we think are important. That's the same as in our observational study. But now we have to decide what are our treatment groups going to be and how many are we going to have. And then we assign the students in our sample to different groups. So you could do this in a lot of different ways. I've decided to make up 3 treatment groups. I'm going to have one group where the students must not do any physical exercise for the whole semester. The second group where they have to work out 30 minutes twice a week, kind of a moderate group or light exercise group. And then a third group where the students have to work out 30 minutes 5 times a week. So I'm assigning them these exercise programs that they have to do. I'm manipulating exercise as our crucial independent variable. Of course, there are other ways that we could do this. This is just one way. And then we observe the students for the semester. We quantify their grades on their final exams, for example, and we make sure that they actually follow the prescribed exercise plan. So let's form a prediction for this experiment. What kind of evidence would support our hypothesis that exercise influences a person's grades? What would the data look like? Well, in my hypothetical study, I've got these 3 treatment groups here, and I might expect to see something like this, where the distribution of grades in the no exercise group is significantly lower than the moderate exercise group, which is also lower than the distribution seen in the frequent exercise group. All right, so moving on, here's a little practice question that we'll look at on Zoom. So I'm going to propose another hypothetical experiment, and I want you to think about what is wrong with the design of this experiment. Okay, so in this scenario, Jane wants to know whether a probiotic pill can help prevent back pain. And she decides that the best way to test this is with an experiment. She designs her experiment to have 2 groups, people who are going to be assigned to take a probiotic pill once a day, and the other group, people who will take a placebo pill once a day. A placebo is a substance that has no specific physiological effect and is used as a control condition in a medical experiment. A common type of placebo pill is a sugar pill. Okay, Jane recruits 50 people for her study. She lists them in descending order by age, and then she assigns the first 25 people to the probiotic group and the second 25 people to the control group. So what's wrong with this design? And how is it going to influence Jane's results? Well, to illustrate that for you visually, imagine these are the people in her sample. We've got adults and young people. And she's sorting them by age and then assigning them into the two groups. So we'll talk about that on Zoom. It all has to do with this idea of keeping things random and representative. So earlier in the course, we talked about random sampling as the best way to ensure that a sample is representative of the desired population. In experiments where we have 2 or more treatment groups, it's also important to make sure that each treatment group is representative of your desired population, and the treatment groups should not differ from each other on average with respect to potential confounding variables. So in experimental studies, we often need to do something called random assignment or blocking. Random assignment is when each participant or subject in an experiment has an equal chance of being placed in any group, regardless of that subject's other characteristics. Blocking is when we evenly distribute the subjects or treatments according to a specific characteristic. Random assignment and blocking can help ensure that you don't build systematic error or bias into your experiment from the beginning. Okay, so we'll talk more about examples of random assignment and blocking in the next lecture for this week. What I want to do next is kind of summarize some potential pros and cons of observational studies versus experimental. I want to say that these pros and cons don't apply universally. They're generalizations, but none of them are universally true. So let's talk about what are the pros for doing an experiment instead of an observational study. Well, experiments are good because the whole point is that you're controlling more variables and really focusing on the key factor of interest, the key independent variable. Experiments often allow you to reduce variation in these other factors. For example, controlling the diet of your subjects, controlling how much sleep they get. Some drawbacks, though, are that sometimes the manipulation we wish to do might be impossible for practical or ethical reasons. We might also overlook important moderators, important other causal factors that only exist under natural conditions. We might overlook including those conditions in our experiment. And we might find something in an experiment that might not extrapolate to more natural situations. And to use the example of our exercise study, suppose in our exercise study we assigned a level of exercise to our group, our treatment group, that was just way more than any university student could do. Like, let's say we assign them like an hour a day, 7 days a week, and that's just not realistic for most university students. Well, it's kind of irrelevant if we find that that positively affects their grades, if nobody can actually employ that. We might also have something called experimental artifacts. These are phenomena that we observe only because of the artificial or prescribed conditions of our experiment. I'm going to suggest a couple of potential artifacts that could happen in our exercise study, but you could brainstorm some other ones. So here are some examples to help you understand what I mean by artifacts. So scenario number 1, imagine exercise really does improve student grades, but maybe it doesn't work when you assign a rigid exercise program that doesn't match a person's natural daily rhythms. For example, let's say in our experiment, we assign the frequent exercisers to wake up at 5 a.m. every day and exercise from 5:30 to 6:30 in the morning. Well, maybe for most university students, this means that you're getting very little sleep, and then it negates any positive benefits of doing the exercise program. And so maybe exercise really does work, but in this experimental design, we would not find any positive effect because we are creating other negative effects with our prescribed program. Okay, as another example, maybe exercise does not affect grades, but our study design caused a boost in grades for other reasons. So for example, suppose the students in the frequent exercise group come in for like a group exercise class and they meet each other and they form a study group and they start studying together and they all do better in their classes because of the study group. Well, in our data, it would look like a benefit of exercise in that group, but actually it was an unintended artifact of like getting students to come out and meet each other. Okay, so coming back to pros and cons, let's do pros and cons of observational studies. Pros, sometimes they can be easier to do. Not always true though. Another pro is that they can be potentially less stressful to the organisms. Also not always true, but it can mean that observational studies are often more ethical. An important pro is that observational studies might be more likely to have validity beyond the conditions of the experiment because we're studying natural variation, and we might be able to avoid experimental artifacts. Cons for observational studies. Well, the biggest one is confounding variables. These variables can make it impossible to deduce cause and effect from observational studies alone. Also, it can be difficult to get repeated measurements under natural conditions. It's very difficult to run observational studies of some processes. Okay, so I want to present a few caveats about cause-effect relationships. So whenever we're trying to interpret a relationship between two variables in a study, we have to be aware of other possibilities. So it could be that variable X causes variation in variable Y, but that's not the only reason we could observe a relationship between them. Here are 3 other reasons. The first one is called reverse causation and mutual causation. Okay, and I'm going to explain what that is with this hypothetical example. So suppose I survey students in this class and I measure how happy you are and I measure how much time you spend outdoors. And suppose I find this positive relationship. The students who spend the most time outdoors are also the happiest. This has been shown in real studies. Well, is it that spending time outdoors causes the students to be happier? Or perhaps being happy causes students to go outdoors, and maybe being unhappy causes students to spend more time indoors. It's also possible that causation could go in both directions. That's mutual causation. That's probably very realistic here. Maybe spending time outdoors makes you happy, and being happy causes you to go outdoors more. So this process of reverse causation and mutual causation is something that we should really consider in any observational study. So any study where we are not manipulating the independent variable ourselves, we have to be aware of the possibility that we could have one of these other causation scenarios going on. Okay, here's another possibility we have to be aware of whenever we observe a relationship. It could be that there's a confounding variable, a third variable that's influencing both of the things we're measuring and that we just haven't considered. So think about, have we considered it? One classic example is the data on Berkeley University admissions that I showed earlier. So there was an association between gender and admission success, but it only appeared that way because of this confounding variable of differences among the departments. Another example of a confounding variable, this is real data on the population growth rate, so number of babies born per town in some German villages, and the number of storks nesting in these different towns. So there's a positive relationship. The towns that have more storks have more babies born. Is that because storks are creating human babies? Well, there's a confounding variable here, and the confound is the number of houses with chimneys where these storks nest, right? So the towns that have more houses have more people, they have more babies born, and they also have more places where these storks prefer to nest. So the confounding variable there is houses. Yet another example of a confounding variable, suppose I go out and collect data on people's skin damage and also the number of days they wore sunscreen in the past year. And I find this positive association. People who wear sunscreen more often have more skin damage. Well, is that because sunscreen causes skin damage? Well, it could be that there's a confounding variable here that I haven't considered. And we can brainstorm a few of them. Maybe a confounding variable is the number of days the person spends at the beach, right? People who spend more time at the beach with skin exposed are going to probably use sunscreen more often and have more skin damage. Another potential confound could be something like latitude. People who live closer to the equator might live in warmer climates where they spend more time outdoors and they have more skin damage as a result. So it's not that sunscreen causes skin damage. It's just that there's this lurking variable that drives variation in both sunscreen use and skin damage. Okay, a third possibility to be aware of is spurious correlations or spurious associations. That refers to times when the association between two variables has occurred purely by chance. Okay, so there's lots of examples of this online. This is real data. This is a time series showing you the number of tornadoes in the world per year and the number of shark attacks observed in the world per year. And so we've got year on the x-axis, and then we've got tornadoes shown in red with the y-axis on the left, and then the number of shark attacks is shown in black. So if you converted these two time series to a scatter plot, it would look something like this. This part is just made up. But what we're seeing here is a positive association. The more tornadoes we have, the more shark attacks we have. Is that because of Sharknado? No, it's purely spurious. Another example, there really is a correlation between the rate of undergraduate enrollment at US universities and the number of injuries caused by falling televisions. If you look at enough variables, you'll find things that are correlated just by chance. It doesn't mean that there's a cause-effect relationship between the two things. Okay, so I want you to think about, of these three possibilities that we covered on the last few slides, we've got reverse causation, confounding variables, and spurious results. Which of those would apply to experiments, and which would apply to only observational studies? So think, would they apply to observational studies, experimental studies, or both? Well, spurious results and confounds can be problems for experiments too, right? So experiments, there's always a possibility that you'll find an effect in an experiment just by chance alone. We're going to see that a little bit later on in this course. The solution to that is to repeat a study, because finding the same result more than once provides really strong evidence that a finding is not spurious. What about confounds? Well, they can be a problem in experiments too. Good experimental design reduces or eliminates confounds. There's no perfect study. Choosing the best approach requires really understanding your study system and thinking about the pros and cons of different approaches to how you could investigate your question. And the best design of a study maximizes the good information that we can get given the resources we have to work with, including time, money, equipment. And again, if we fail to design our studies well, we waste our time and resources. And some of the best studies combine evidence both from observation and experiment, sometimes even within the same scientific paper. Okay, so very briefly, I want to talk about a few other types of studies. When you read scientific papers, most of them are either observational studies or experiments, but there are other types of papers as well. One of the major types is reviews and systematic reviews. And if you go on to write a thesis or do a major research project, reviews are often a great place to start your investigation of a topic. A review article or a literature review is an article that summarizes the current state of our understanding of a topic, and it brings together lots of evidence from many previous studies. It does not report on new data. And so here's just a screenshot of an example of a review article. This one is on theories for why people age. A systematic review is a special kind of review that answers a defined research question by collecting and summarizing all of the evidence that fits a pre-specified criteria. And the goal of a systematic review is to provide a much more complete summary of the current evidence on a given topic. So it's very similar to a review article, but instead of being a little bit more open to the author's interpretation, a systematic review is designed to be systematic and include everything that might apply to that topic. And these are very commonly used in medicine, but they're increasingly used in other fields as well. And so this is an example of a systematic review from some kind of medical journal. Okay, another type of study to be aware of is called a meta-analysis. A meta-analysis is a study that combines quantitative results of many previous studies on a given question, and it uses statistics to find the average or the overall effect. So in order to do a meta-analysis, you need to have a whole bunch of previous studies on that topic. And also, the measurements in those previous studies need to be similar enough that it would be reasonable to combine them. For example, we're going to look at one on the next slide, a meta-analysis of the question as to whether caffeine improves athletic performance. There have been scores of studies on this question where athletes have been either given caffeine or given a placebo, and then their athletic performance is tested. And this is a figure from a meta-analysis or a graph from a meta-analysis summarizing this information across all these previous studies. So each of the rows in this really big figure is a different study, and these are studies that compared caffeine versus a placebo. And these dots and whiskers represent the overall effect found in each of these individual studies. And if you look really closely, the axis at the very bottom of the slide has 0 in the middle. So if a dot is on 0, that means a study found no difference between the caffeine group and the placebo group. Negative data points here represent a study that found that the placebo group performed better than the caffeine group. And positive values show that a study found that the caffeine group performed better. So this figure summarizes all those previous studies, and at the very bottom is the meta-analysis, the pooled result. And so what that does is it mathematically combines all of the previous estimates to give a really good idea of the overall effect. And this particular meta-analysis found that on average, caffeine has a slight boosting effect on athletic performance. Okay, and one more type of biological study is mathematical or theoretical modeling studies. These provide a formalized description of a system, for example, by building a system of mathematical equations. For example, we've got a lot of papers now. Well, historically, there have been many papers doing this for other diseases, but for COVID, there's just been a flourishing of papers mathematically modeling the spread of contagious disease. We might also have modeling studies that model what the climate will be like in the future in some particular part of the world. Okay, so let's wrap up with just a few practice questions that we'll take up on Zoom. Here's another scenario. Suppose I'm interested in the study, in the question of whether kids who go to daycare get more colds than kids who stay home with a caregiver during the week. And suppose I collect data on the frequency of colds among kids in 2 groups. In my first group, I am sampling children who stay home with a babysitter. And I get a random sample of 32 children, each from a different household. The households are randomly sampled from a list of all households with children in Ottawa. In my second group, I've got children who go to daycare. Conveniently, there's a daycare on Carleton campus with 24 preschoolers, so I it's going to be very efficient for me to go to the daycare and use all those 24 kids as my sample for group number 2. Okay, so questions to practice. First of all, is this an observational study or an experimental study? Second, what are the dependent and independent variables? And third, what do you see as a problem with the study? Is the sampling method adequate? And to give you just an illustration of what this method is like, in my group number 1, I've got one child from each of these different households. And in my group number 2, I've got children from this one daycare. So imagine what happens when a virus is introduced to any of these groups. And take this illustration here as a hint for what might be a drawback of this particular study. Okay, here's another practice example. Suppose we have the question as to whether vitamins, like really high doses of vitamin C, cure a cold. You can pay a lot of money in the drugstore for these like cold effects remedies that you're supposed to take when you start getting a cold, and it's supposed to boost your immune system. Well, you can also just like eat a whole lot of oranges, but suppose we want to test this question in our class, and we decide to run our study by finding people who are just showing the earliest signs of a cold. And for anyone who comes down with a cold, within 2 hours of their first symptom, we're going to make sure that they take cold effects as directed on the package. And then we monitor their symptoms over the next week. So first question, is this an observational study or an experimental study? And second, suppose we get data like this. So in this slide, we're seeing data from like 3 people in our sample. So these 3 people on Monday started to get a cold. They started to take the vitamins, and then we're kind of graphing their severity of symptoms over time, over the following week. So these 3 people got colds, and they took their cold effects. And the question is it working? Is there enough information here to tell if it's working? And I've only shown a sample size of 3 here, and that's just because it takes time to make these illustrations. What if I had 300 people in this sample? Would there be enough information to tell? Would a sample of 300 with data that look like this, would that be able to tell you whether cold effects cures a cold? So we'll talk about that on Zoom when we meet on Thursday. Just as an aside, cold effects got in a lot of trouble in 2004 because it turned out that they had data, studies of their own product, and they were cherry picking the data that they presented to the public. So they collected lots of data, and the data that didn't show that cold effects had a good effect, they buried. And the data that was favorable to cold effects, that was the data that got released. If you're interested in thinking about science done poorly and how to do science well, these are a couple of books that I highly recommend. Okay, I'll